Welcome to Lesson 5 in our Study of Time series. We've been studying the theory of regression, and we're going to study some more of it today. We still have some to cover, but we're going to mainly bring it to a close this time, mostly at least. Next time, we'll work out some examples. We'll show lots of graphs. I'll even demonstrate doing much of it with the R statistical language. I expect that for most of you that'll be more entertaining. I hope it'll even be more enlightening. And we'll get into how one goes exploring data, how one chooses what model to use. In short, we'll get our hands dirty with some actual data. I think that'll be a lot more fun than all this theory, at least for most of you. I have to confess, for me, the theory is the most fun part. But we need to know enough of the theory to know what we're doing and why. So bear with me, get through the remaining regression theory, and then we'll dive into the deep end of the pool. We will start with weighted least squares. Sometimes the noise doesn't have autocorrelation, but it's still not white noise because different noise values have different variances. This might happen, for instance, if the noise is measurement error, but different measurements are taken with different instruments that have different levels of precision. Or we might even know what the different variances are. Suppose we know that the variances of the noise for observation alpha is sigma alpha squared, but different noise values are independent and follow the normal distribution. The variance-covariance matrix of the noise is no longer proportional to the Kronecker delta. It's no longer some constant times the identity matrix. It's now some other matrix, but it's still diagonal because there's no autocorrelation. But the diagonal elements are the variances of the individual observations. The probability density function for noise value alpha is given by the normal distribution, and we're assuming it's zero mean. The joint probability density function for all the noise values is the product of the individual PDFs. This expression can be written as a sum in the exponential, and the negative of its logarithm is given by this. The relevant part is that it involves this sum of the squares of the noise values divided by their individual variances. Now, we used to have a very similar expression when we did ordinary least squares, but all of the noise values had the same variance. Now they don't, so there's a different variance in each term in the sum. By the way, you don't need to apply an Einstein summation convention for alpha in this term because the summation is already explicitly written out here with the summation sign. We're going to estimate the noise values as residuals from whatever model it is that we're applying. Then we will maximize the log likelihood by minimizing the total sum of squared residuals divided by their variances. Now, this isn't just the sum of squared residuals. It's the weighted sum of squared residuals weighted by the inverse variances. So it's a weighted least squares with weights given as 1 divided by the variances. Now, we used to be able to write this quantity compactly with the Einstein summation convention, just as the sum of each residual times itself. How are we going to do that now? Well, we actually can in a compact form with the Einstein summation convention, but to do so, we're going to define a weight matrix. It is a diagonal matrix, but the diagonal elements are the inverses of the variances for the individual noise values. Note that this particular matrix is the matrix inverse of the variance-covariance matrix. The weights assigned to each data point are 1 over sigma 1 squared, 1 over sigma 2 squared, etc. Note that if there is low variance, so that the noise isn't very big, we give that high weight, which makes sense because an observation with very little variance that will be very precise should be given greater weight in our regression fit. The ones with high variance have low weight, and that too makes sense because if something has very high variance, so it's very uncertain, we should give it low weight when we're computing our regression. The total squared error can now be written this way using the Einstein summation convention. We sum over all values of alpha and over all values of beta. Since this particular quantity, the weight matrix, is diagonal, the only terms that survive in the double sum, there are two repeated indexes, are those for which the indexes are equal, the diagonal terms. So we end up with exactly the same sum that we had here, only now it's written in this sort of compact notation, which I'm very fond of and which I regard as being very helpful. By the way, do take note, once again, I'm using beta, the Greek letter, as an index, even though I will also use it as a variable for the parameter values. I know it's not the best form. It is what I'm used to, however. I hope it's not too confusing for you. Keep in mind, it's a foible of mine. I probably ought to change my ways, but don't hold your breath waiting for that to happen. Now, the matrix G sub alpha beta is the weight matrix. We can also call it the metric tensor. Those of you who have studied general relativity will know what that means. Those of you who haven't, don't worry about it. Let's recall that the residuals from a linear model are just the differences between the data values and the model values, the model without the noise. So the sum of squared errors is the metric tensor times the residual times the residual, and the indexes with the Einstein summation convention tell us how all of the sums need to be run. Well, once again, we're going to find the parameters by taking the partial derivatives of the squared error with respect to the parameters. That gives us this expression here, and we're going to set it equal to 0 to get the best parameters. We can rearrange that to form this equation. I just brought two terms on different sides and divided by 2 because I didn't really need to have that there. Now, we used to define an S matrix, where the S matrix element AB was the inner product of trial vector A with trial vector B. Now, let's define it as a weighted inner product. So we will use this expression. It's metric tensor or weight matrix defining weights and defining sums over values of trial vectors for trial vector A and trial vector B. This is part of a general strategy we're using for weighted least squares, that instead of using inner products of n-dimensional vectors, we're using weighted inner products. The defining equation then becomes S matrix times parameters gives weighted inner product of trial vector with data values. Well, we can solve that the same way we did before. We will compute the inverse of the S matrix, and then we can say that the parameter values are the inverse S matrix times the weighted inner products of trial functions and data values. Now, previously, we had some interesting properties of what we called dual trial vectors. I'm going to define dual trial vectors again in exactly the same way. It's just that dual trial vector A is the S matrix, the inverse S matrix times the trial vectors. And then we can simplify our expression to say that the parameters are simply the weighted inner product of the dual trial vector with the data vector. Now, these new dual trial vectors have some interesting properties. They had interesting properties in ordinary least squares. They have some very similar properties. For instance, with our new definitions, the weighted inner product of a dual trial vector and a trial vector is the Kronecker delta, the identity matrix. It's the same as before, but we're using weighted inner products instead of ordinary inner products. Also, the weighted inner product of a dual trial vector with another dual trial vector gives an element of the inverse S matrix. This too is just like we had before, only now we're using a weighted inner product instead of an ordinary inner product. Everything's going to run very similar. All we have to do is transform all inner products of n-dimensional vectors to weighted inner products. For instance, when the data actually follow the model, the difference between the estimated and true parameters difference between estimated and true, which I've called delta beta sub A. It's the weighted inner product of the dual trial vectors with the noise values. The variance-covariance matrix of the parameter estimates themselves, in this case, is just equal to the inverse S matrix, which serves to emphasize the importance of the S matrix and its inverse when doing least squares. By the way, originally we had that the variance-covariance matrix was sigma squared times the inverse S matrix, because we have to include the noise variance in our estimate. Well, now we have to include the fact that there's a different noise variance for every noise value. But remember that our S matrix involved a weighted inner product. The weight matrix itself included the variance information, so the variance information is already built in to the inverse S matrix.